Hello, my name is Roman Obermaisser from University of Siegen, and in this presentation I would like to present an architecture from Mixed-Criticality Systems, and this result is part of the European project DREAMS. Before presenting the architecture, let's have a look at Mixed-Criticality Systems. There is a trend to Mixed-Criticality Systems in many domains, for example in avionics, industrial control or healthcare systems, and the major reason is that in many domains we have increasing functionality, and this results in higher numbers of node computers and networks, and also a tremendous effort in cabling. And in order to tackle this problem, we need to combine functions on shared node computers. We also need to use shared networks. And if we do that and we have applications where functions with different criticality are present, consider for example a car or an airplane, then we end up with mixed criticality systems. That means we share a computing platform for both safety relevant, safety critical and non-safety critical functions. Consider for example a car where you have a broad spectrum of criticalities ranging from entertainment and comfort functions to safety functions that have a direct impact on the safety of the passengers of the car. In this architecture that I would like to present, we look at the logical view and the physical view. As you can see here, on the left-hand side we have the logical view where the overall application consists of subsystems. These subsystems can have different criticality levels, as indicated by the colors on this slide. So we have, for example, a safety critical red subsystem and a non-safety critical green subsystem. These subsystems can further be structured into components which then interact using interfaces. On the right-hand side of this slide, you see the physical view. In this physical view, you have different computational nodes that host components of different criticality levels. So that means each node computer is a shared resource where nodes, both green ones and red ones of different criticality levels, need to coexist. And likewise, also the communication networks, they also serve as a shared resource for different functions of different criticality levels. What's the purpose of an architecture in this context? Well, an architecture provides on the one hand side an architectural style with rules for defining a mixed criticality system. That means the architecture defines how you structure the system into components, how you define the component interactions and the interfaces. And in addition, the architecture also provides a platform. And this platform provides architectural services as a stable foundation for the implementation and integration of components in such a way that the global application services can emerge from the local services of the components. Consider, for example, a control function, something like a braking system in a car, where you have local components like sensor components, actuator components, controller components, each providing local services. And what we need is a platform for the integration of these components so that the global services can emerge from these local services, such as the automotive braking service in this example. The platform supports this process by providing architectural services, for example, communication services, fault tolerance services, diagnostic services, in such a way that these services can be validated beforehand and they don't have to be redeveloped and revalidated in every new application from scratch. So therefore, these platform services significantly simplify the development of the applications. And via this platform, the components can then interact using the linking interfaces that you see on this slide on the right-hand side. Challenges for such a platform include now key points that you see on this slide. On the one hand side, we need to deal with the temporal unpredictability of multi-core platforms. Multi-core platforms are now becoming prevalent in the area of embedded systems. And when we look at commercial off-the-shelf multi-core platforms, then these platforms are a source of indeterminism because there are cache hierarchies, there are bus arbitration policies, which means that the application in one core can affect the temporal behavior of applications in other cores. And this is in particular a problem for mixed criticality systems, where we have applications of different criticalities on the same chip, and we would like to prevent that one function, in particular of low criticality, affects other functions of higher criticality. A second issue is the interconnection of multi-core processors. When we use multi-core platforms, when we use multi-core chips in embedded systems, then usually we need more than one multi-core chip. On the one hand side, we often have resource requirements that exceed a single chip. So that means we need higher computational power. And in addition, we also have requirements for reliability that often exceed the reliability that we can get from a single multi-core chip. If we look, for example, at ultra-dependable systems where we demand only one failure in 10 to the power of 9 hours, then this reliability can only be achieved by using fault tolerance at the system level, where we combine many multi-core chips and where we implement fault tolerance at the system level. And the third key challenge that I'd like to point out is heterogeneity. So in case of architectures for mixed criticality, we need to also satisfy dissimilar requirements when it comes to the timing, when it comes to the models of computation. For example, a model of computation for a multimedia application is different to the model of computation that you use for a control application. Whereas control applications are typically based on cyclic time-triggered interactions, you have data flow models or client-server interactions in case of multimedia subsystems. I would in particular like to highlight the need for the segregation and partitioning, which is a core part in meeting these three challenges. And this is a key part because in a mixed criticality system, we want to certify each application system to the respective criticality. That means when we combine functions of different criticality on a shared platform, then we want to separate the safety arguments. So it doesn't make sense to integrate safety critical and non-safety critical subsystems if this would mean that every subsystem would become safety critical, because the cost involved in certification for safety critical subsystems is significantly higher than the certification cost for non-safety critical ones. Therefore, we need to compose the safety arguments of individual subsystems, and we need to focus the certification efforts on the most safety relevant subsystems. This is something that is supported also by major certification standards. For example, IEC 61508 introduces compliant items with independent safety arguments, but it also points out that all the hardware and software must be treated as safety related unless there is credible evidence that points out that there is sufficient independence between these subsystems. That means, looking again at this picture of the logical and the physical view, if we combine components with different criticalities on such a shared platform as you see it here, then these subsystems, these components, should not interfere with each other. This, first of all, refers to fault containment. So fault containment means that we have a delimiter of the immediate impact of a fault, and this means that each component should provide a fault containment region, in particular when it comes to design faults. That means two components of different criticality levels should be independent fault containment regions with respect to design faults, in such a way that a design fault of one component will not affect the ability of another component to provide its correct services. This is important also because there is typically a higher residue of design faults in non-safety relevant components due to the reduced rigidity of the development process. In addition to fault containment, we also need to look at interference, which is not related to the faults of the components. That means if we combine components on a shared platform, then we either need to prevent interference, this would be the ideal case, or at least we need to bound the interference between the components on a shared platform. That means if we combine two components on a shared platform, then the effect that one component has on the timing, on the execution time of another component needs to be well known in advance in order to provide the safety arguments in case of real-time requirements. And this is needed for different types of resources, including memories, including the interconnect, including also the input-output resources, the processor resources, as a prerequisite for modular certification. A technology that is well known to provide this temporal encapsulation, to provide fault containment, and to avoid interference is time-triggered control. And this is a technology which uses a global time base in order to control the start of communication and computational activities, which is well established in different domains for safety critical systems, for example in avionics and automotive, and which can be found at different integration levels. For example, we can see the use of time-triggered control in case of operating systems and hypervisors, where time-triggered partitioning using cyclic schedule tables is used to schedule the execution of partitions. That means, according to a schedule table, partitions will be executed in a cyclic manner, thereby ensuring that there is the absence of interference or bounded interference between different partitions. As you see here on this slide, we have 3 partitions with different criticalities as indicated by the color coding, and the hypervisor or the operating system provides the cyclic schedule for the temporal partitioning. This is something that can also be found in existing hypervisors in products, for example Xtraton, PikeOS, LynxOS or VxWorks, where such a cyclic schedule is being used. Likewise, time-triggered control is also used at the cluster level. If we look at off-chip networks, then we have time-triggered protocols like time-triggered Ethernet, TTP or FlexRay that provide fault containment and that prevent interference between node computers at the level of off-chip networks. On this slide you see a dual star topology where you have 2 central guardians that are equipped with a priori knowledge about the permitted behavior of the node computers in such a way that one misbehaving node computer cannot interfere with the correct behavior of the other node computers, neither in the time domain nor in the value domain. And this is made possible by time-triggered schedules that are deployed in these central guardians. This is something that is supported in the avionic domain, for example using TD Ethernet, or in the automotive domain with protocols such as FlexRay. And a third area where we support time-triggered control is the chip level. So we have architectures that are based on time-triggered on-chip networks. Here you see an example of such an architecture. That's the architecture based on the time-triggered network on a chip, where we have an on-chip network where messages are exchanged based on time-triggered schedules. And the network interfaces in this picture, they are equipped with time-triggered schedule tables. And they inject messages at points in time that are coordinated among the different cores in such a way that there are no collisions and that there is no contention at the level of the on-chip network. In the time-triggered network on a chip, we use source-based routing based on predefined temporal and spatial resource allocations with different network topologies. So it's possible to use a mesh topology, for example. And we make sure that the different paths that the message takes through the routers of the on-chip network, these paths do not collide at a certain point in time with the paths of messages of other components. Thereby, we also gain fault containment as well as absence of temporal interference between different components. What we provide in the DREAMS architecture is now an architecture that combines these different integration levels. That means we provide an architecture that combines the chip level, that combines the level of the on-chip networks with the level of the hypervisors, of the virtualization of the computational resources, with the level of the off-chip networks. And we support that based on a waistline architecture that is inspired from the area of the internet. So you might know that in the internet we have the waist, the internet protocol, with many underlying implementation options, ranging from different kinds of protocols like Ethernet to other protocols that you use for internet access, including also wireless protocols. And we also have a high number of higher protocols that build on top of IP up to reaching certain application areas. In a similar way, we structure our architecture for mixed criticality systems. We provide a domain-independent waist, which includes a fault-tolerant global time base, which includes secure and timely communication services, execution services, and integrated resource management. These services focus on time and space partitioning. That means these services establish the absence or bounding of interference and also the establishment of fault containment. Nevertheless, they can be realized based on different underlying implementation options. On top of this wasteland architecture, we realize optional services that refine the services of the waste for different applications and different domains. And then at the top level, you can see in red different applications for different application domains. For example, healthcare, avionics, and wind power. These are the domains that we support in the DREAMS project. I would also like to give you a glimpse of how we map this wasteland architecture to the actual platform of network multicore chips in the European project DREAMS. You see on the left-hand side, on the top left-hand side, the wasteland architecture, and on the right-hand side, you see an architecture of networked multicore chips with the same color coding. So you see the waste in yellow. So these are the services that are domain independent and that ensure the key architectural properties of DREAMS, in particular time-space partitioning. And you see on top of the waste the optional architectural services in blue, and finally the application services in red. And if we look at the right-hand side, then we can start at the cluster level. And at the cluster level, we have off-chip networks that are used for the interconnection of node computers. We then zoom in into one of these node computers. One of these node computers consists of different application tiles that are interconnected by an on-chip network. So this on-chip network supports the interaction between the application tiles. And you also see that we have zoomed in into one of the application tiles. This gives the view on the left bottom side of the slide, where we have the DREAMS virtualization layer, the operating system, the hypervisor, that establishes different execution environments, different partitions, where we can execute the application services, where we can execute the local services such as provided by the application components. Based on the color coding, you see how the different elements of the wasteland architecture are realized. You see, for example, the yellow services, the communication services are realized by the off-chip networks, by the on-chip networks, the on-chip interconnect, and also by the gateways. On the one hand side, we have off-chip, on-chip gateways at the chip level, but we also have off-chip gateways between different off-chip networks in order to support the coupling of different off-chip networks with different protocols, for example. In addition, we have the execution services. These are realized within the application tiles. They are provided by the DREAMS virtualization layer by establishing the partitions. And you also see the optional services which can be realized either as system tiles realized in the hardware with dedicated tiles. They can be realized as system components within an execution environment established by the hypervisor, or they can be realized within a partition where also an application component is present as middleware services. And furthermore, you see the application components depicted in red in the system tile, in the application tile. And you see that these application components, they can use the different services, including the optional services. They can use the services of the system components, but they can also use the services of the system tiles using the on-chip network. And in this DREAMS architecture, it's possible to have interactions, to have global services that involve application components that are located on different multi-core chips, on different application tiles, in different execution environments, different partitions. And for that purpose, we provide an end-to-end virtualization of the resources. That means an application component can communicate via the hypervisor, via the on-chip network, via gateways and off-chip networks with a remote component that is located on another multi-core chip in another partition. That's a key focus of the DREAMS project. Let me conclude by pointing out that there is an increasing importance of mixed criticality systems based on network multi-core chips. In these architectures, we have key requirements that involve partitioning heterogeneity and adaptability of these mixed criticality systems, we at the moment see that we have solutions at different integration levels. For example, we have time-triggered systems at the cluster level, at the chip level, at the level of operating systems and hypervisors. A key challenge is to combine these different integration levels into one architecture, and this is what we do in the DREAMS project. So we address end-to-end systems engineering by combining the cluster, chip, and hypervisor level into one overall architecture, thereby providing a system perspective of mixed criticality. Thank you for your attention.